So last time we talked about climate change and why it's important to stop emitting carbon dioxide into the atmosphere. One solution to that is carbon dioxide capture and storage. So here is a power plant that is driven by natural gas or coal, a fossil fuel. Burning natural gas or coal to produce electricity will emit carbon dioxide into the atmosphere. Instead of taking the flue gas from the coal or natural gas that's burned and emitting to the atmosphere, we can instead try to selectively capture the carbon dioxide out of the flue gas and then compress it to where it becomes a supercritical fluid and pump it underground under a geological reservoir. And so this rock here, this bedrock, will prevent the carbon dioxide from escaping into the atmosphere where it can instigate climate change. So this is a long-term storage solution of carbon dioxide. And over timescales that are tens of thousands of years, this carbon dioxide will eventually turn to rock and be permanently stored there. So the subject of this is the carbon dioxide capture and separation plant. So we have the flue gas coming out of the coal-fired power plant that consists of carbon dioxide, around 15%. The rest is mostly nitrogen. It has some water, which can be condensed out. There's sulfur dioxide, nitrous oxides. Those are often taken out anyway. So we can kind of think of the flue gas as comprised of nitrogen and carbon dioxide. So it's about 85% nitrogen and around 15% carbon dioxide. And the goal is to take away the carbon dioxide, separate it out, because you can't, if you pump up the nitrogen, it's not going to turn into a liquid. It'll remain as a gas. And there wouldn't be enough room for nitrogen underneath in the geological reservoir. So we need to capture it first. So one way that you can capture it is through an absorption process. So the idea is that some solvents, liquid solvents, absorb CO2. So what that means is CO2 readily dissolves into these solvents and enters the bulk liquid phase from the gas phase. And one popular solvent for carbon dioxide capture is MEA. It's an amine-based solvent, and carbon dioxide interacts with the amine very strongly and binds to it. And then another important principle is that if you heat up this solvent, heat up this liquid, not to the point where the solvent boils, but just heat it up, less carbon dioxide will be absorbed inside of the solvent, and therefore carbon dioxide will be driven off of the solvent into the gas phase. So this is a way that we can regenerate the solvent. So once we have the solvent and once it's saturated with carbon dioxide, we can heat it up and drive off that carbon dioxide to recover it. And then we can use the solvent again for another round of capturing. So this is what a process would look like. So here's your carbon dioxide capture and storage plant, right? And so here we have our flue gas, okay? So it's going to enter this column. So this is CO2-rich feed gas. Flue gas. Okay, and this is, you can abstract it as a nitrogen carbon dioxide mixture. Okay? And the first unit is an absorber. So this is an absorber. Okay? The goal of the absorber is to take this flue gas and remove the carbon dioxide. So then what comes out of this is lean gas. So exiting out of here, this is called lean gas. And by lean, that means the carbon dioxide is removed from it. So this is lean gas, mostly N2. Okay, so the CO2 has been removed at this point. And the way that you remove the gas is by passing fresh solvent through the column. So right here, this here is lean solvent. And so lean, again, means the lack of CO2. So this is lean solvent. So this means it's fresh solvent or CO2 depleted solvent. So there's no CO2 in it, and it's ready to absorb CO2. And so the solvent trickles down through the column, right? Trickles down through the column, and by the time it gets to here, it's saturated with carbon dioxide. So this is rich solvent right here. So this here, this is rich solvent. And it's rich with CO2, so CO2 rich. So the idea is you pass in this fresh solvent. The solvent absorbs the carbon dioxide from this mixture, right? And then pure nitrogen exits, not quite pure, but lean nitrogen, lean gas. And then the rich solvent, the solvent with the carbon dioxide, then leaves the absorber. So that's the idea behind the absorber. So this would be extremely expensive if you couldn't reuse the solvent. So what happens is, so here's your solvent right here. I'll highlight this. So what happens is you take the rich solvent and it goes through a heat exchanger, okay? All right, so here's the rich solvent. And so also, the rich solvent enters here. So this is rich solvent right here. And the rich solvent enters what's called the stripper. So this is the stripper. And the goal is to regenerate the solvent. So what will happen is this rich solvent comes down through here, right? So it percolates down through the column, and it comes to this, and this is a reboiler, okay? This is a reboiler. So this here is steam, and it's a reboiler. So I'll highlight this. All right, so it's a reboiler, and it heats up the solvent. So the solvent at this point is very hot, okay? And by the time it comes down here, the carbon dioxide will have been driven off because it's hot. So it's hot, it dries out the carbon dioxide, and the carbon dioxide exits right here. So this right here is where the carbon dioxide comes out, CO2 gas. So this is where you recover it. And finally, you to sequester. Okay, and then you compress this CO2 gas that comes out. It doesn't have any nitrogen in it. It becomes a supercritical fluid. You can store it underground where it can't instigate climate change. So this here, this is a condenser. So this is a condenser. All right, so what flows through here is cooling water. So this is cooling water. Oh, well, actually, yeah, so then the cooling water in, this is the cooling water in, okay, and this is cooling water out. I'm not sure which, so you could probably switch these. I'm not sure which is which. It's not clear from the diagram. So what's happening is this is hot, okay? So at this point, this is hot solvent. So, let me highlight this. So by the time the solvent gets to here, it's really hot, okay? So it's hot, but it's also depleted of carbon dioxide. So it flows through here, and this is a heat exchanger, all right? I'll explain that in a second. And then this is cooling water going through here to make it cold, all right? So this is the lean solvent. So by the time the solvent gets to the reboiler, it's hot. So this is hot and CO2 free solvent. So right here it's hot, right? Because the reboiler heated it up to drive off the carbon dioxide. But then right here, this is cooling water. So I'll put CW for cooling water. And now the solvent is cold because it has to be cold so it can absorb carbon dioxide. All right, and this heat exchanger here, D, this is, well, let's think about this. This is also cold, right? It's relatively cold here, right? And this is hotter now, right? because what happened is this cold stream here exchanged heat with this extremely hot stream, right? And it got hotter. And that's good because in this stripper, we want the solvent to be hot, so it lets go of the CO2, okay? So the goal of the stripper is to regenerate the solvent and remove the CO2 from it. The goal of the absorber is to pull the CO2 from the gas, okay? So stripper to regenerate solvent. So stripper removes regenerate solvent. i.e. drives CO2 from it. Okay, and then the absorber removes carbon dioxide from the gas. So those are the primary goals of it. So yeah, so these are two parts. Yeah, and I think that's all I want to say. And check out Chapter 5, the intro, for a very detailed text on this. In your homework, I linked to this. Yeah, so I guess I should say also the purpose of the condenser. So this here, you have hot solvent coming up, but then here, you have solvent reflux. So the solvent comes down, so it can trickle through the column again. And the condenser is just helping the carbon dioxide gas escape from the solvent. Okay, so what do these trays look like? See these trays here? Right here. So I'm going to zoom in on one of these trays. So this is a tray. Okay, so here's our tray, and each tray here has liquid holdup, and that's thanks to the weir, okay? So the weir is this part right here. So this part here is the weir. Also seen right here. So this is the weir. Right, so those go inside of the column, and then you have liquid holdup, and the liquid level is whatever height the weir is. And then in a countercurrent flow stream, the liquid, well, it flows down, the solvent flows downwards, and the gas flows upwards, so it's countercurrent. And then gas bubbles through these holes in the tray, and this maximizes gas-liquid contact and encourages mass transfer from the gas phase to the liquid phase. The mass transfer here is the carbon dioxide. So you can see here these little bubbles of gas inside of the liquid holdup. And then you can see the liquid holdup here. This is the liquid on each tray, and then it flows down like that. And there's a video in the book of one of these. So let's develop a dynamic model for the CO2 absorption column, okay? So first, I want to outline the intimate mixing assumption. And that's basically that the carbon dioxide in the gas phase is in a thermodynamic equilibrium with the carbon dioxide in the liquid phase. Okay, so this is the intimate mixing assumption. And this is really through the design of the trays where gas can bubble up like that. So C2 in the gas phase is in thermodynamic equilibrium with the absorbed CO2 in the liquid phase. Okay, so let's define a stage here. So let's let this is defined to be stage I. Okay, and let's let Xi be the concentration of carbon dioxide in the liquid, and Yi the concentration of carbon dioxide in the gas. Henry's law assumes thermodynamic equilibrium between the carbon dioxide in the liquid and gas phase. And the relationship then is through Henry's law, is that Yi equals some coefficient, which is Henry's constant, times xi. Okay, so I'll label these. So this is the mole fraction, well, mass fraction. In the liquid phase, and this is in the liquid holdup. So this is the Henry's constant. And then the other variable, y, this is the mass fraction in the gas phase. Okay, so maybe I'll draw these different colors to correspond. So this is yi. Yeah, this is yi. This is in the gas, in the vapor. And then this is in the liquid phase, xi. Yep. Yeah, so this is Henry's law. So it's basically, so if you plot the two, so I like to plot them often. So if this here is xi, and, oh, sorry, this is yi, and then we'll put xi here. These are linearly related, okay? And the slope is the Henry coefficient, okay? So that's the slope, and I'll draw this in green. Slope is the Henry coefficient. So basically, if the concentration of CO2 is very high in the gas phase, then it's going to be high in the liquid phase, and vice versa. So high concentration, well, I can say that more precisely. Concentration of CO2 in liquid and gas phase are linearly related. Which is very intuitive. So that's Henry's law, and we'll invoke this. And so if in contrast, liquid are flowing really fast through there, or there wasn't a lot of contact between the gas and liquid, and there wouldn't be time for the CO2 to reach thermodynamic equilibrium, Henry's law wouldn't quite hold. And then it gets really complicated, but this is a good approximation. Okay, so now we want to write a mass balance on stage I, so we can derive a set of ODEs that describe the dynamics of how the concentration in the liquid and gas behave. So we need to find a few variables here. So let's let L be the flow rate of liquid down the tray. So this is the mass flow rate of liquid solvent through the absorber. Okay, so you can see right here, this is L, and it's the liquid that's falling down from that hold-up tray into the next stage. And let's let G be the mass flow rate of gas through the absorber. All right, so I'll highlight this now. So here's G, all right, and G, see it's flowing up into the tray through those holes, right, and then there'll be little gas bubbles. So there'll be little gas bubbles in there. Yeah, and the flow rate at which that happens is G, okay? All right, and let's let H be the amount of liquid hold up on the tray. So this is the mass of liquid on the inside the tray. On each tray, and this is constant because of that weir. So because of that weir, that keeps the volume constant. It's like an overflow line in a reactor. So this, highlight right here, this is the liquid holdup right here. All right? And then xi, just like before, xi is a property of the liquid holdup on, now this is a function of I, which stage, because let's think about this. Think about it. So this stage right here, the concentration of CO2 and the solvent is going to be maximal because think about it, the solvent's been traveling down, right? And it's experienced the highest concentration of CO2 right here. By the time the solvent gets up here, by the time the gas gets up here, sorry, it's not going to have much CO2 in it. And so the thermodynamic driving force for driving CO2 in the solvent is not very high. So what you're going to have is a low concentration of CO2 in the solvent here. So basically, xi is going to change from stage to stage. So is yi, is the CO2 is stripped from the gas. So this is, and that's why I decorated this with I. So this is mass fraction in the liquid phase. And then yi is in the gas phase. So this is in the gas phase. So here's yi. I like that one. This is yi. This is the gas phase, stage I. Okay, so now let's write some ODEs that govern all of these. And I should note one other approximation is G is constant here. And it kind of doesn't make sense, right? Because you're removing CO2 from the gas, yet we're saying G is constant. It's definitely an approximation. And maybe in one of your classes, I know I did my undergrad, we relaxed this assumption that G is constant. And now G is also decorated with I because it's different in each stage as CO2 is stripped from the gas. That makes it a more difficult problem. So it's a good approximation. All right, so if we're making a mass balance, we always need to define our control volume. So let's define our control volume. Stage I. This is our control volume. All right. And let's write an ODE for this. Well, we have accumulation. So the question is, how much is accumulating? So how much CO2 is in the liquid? There's H, xi, okay? And what we're going to do is neglect the amount of CO2 in the gas right now. Okay? Okay, and this is equal to in, so how much is going in, which is G, and then yi minus 1. That's the amount of CO2 that's entering it. But there's also liquid from the top stage that's flowing into it, right? And that's L times xi plus 1. Right? So let's see if I can highlight these to help guide you. So this is G, and that's this, right? This is CO2 entering right there. And let me underline this. So L xi plus 1. This is the liquid crossing right here, right? And the liquid composition is xi plus 1 because it's coming from that tray above it, right? And then there's also stuff leaving it. So there's minus L xi, and that's the liquid holdup from that particular tray leaving. So I'll underline this. Whoops. So this color, L xi, and that's this. That's this liquid leaving, okay? And there's also gas leaving right here. This gas from stage I is leaving. That comes with a minus sign. So minus G yi. Okay? And this ODE contains both xi and yi. But let's remember that we're assuming that yi and the xi's are related, right? And we're really interested in knowing what the composition of xi is, what the composition of CO2 in the liquid holdup is. And so what we'll do is invoke our Henry's law approximation, right? To eliminate the yi's. And so one, we know this one, via our intimate mixing assumption, and we know this one, right? So this one equals A with our Henry coefficient, xi minus 1. And this one equals A xi via Henry's law. Okay? And the liquid holdup is constant, so we're going to take this out, right? Okay? And then what we get is H dxi dt is equal to G A xi minus 1 plus L xi plus 1 minus L xi minus G A xi. And we'll collect the terms involving xi here, which equals G A xi minus 1 plus, oops, I'll put a minus sign. Factor out that minus sign. Minus L plus GA xi plus L xi plus 1. And voila, there's an ODE that governs the concentration of carbon dioxide in the liquid holdup tray of stage I. So this is it. So ODE for xi equals xi of t. Okay, so this is the dynamics of xi of t. And its first order with respect to itself, you see xi. And then there are two inputs here. So this is kind of the state variable. So let me highlight this. Use some nomenclature. So this is our state variable. State variable. Because it's telling us about the state of stage I. Now the other two are inputs. This is the input from the gas below, and the second one is the input from the liquid above. Okay, so these are inputs. This is an input. Okay, so this is actually coupled to an ODE for the stage above and below it. So they're all coupled together. So this is coupled to ODEs governing other stages. Okay? And so we can make this in a nice form involving time constants if we define tau to be H over L, and we define S to be AG over L. So this here is called the stripping factor. And tau is the residence time on a tray. So it's a volume divided by a liquid flow rate. So that's the average time that a molecule of the solvent will spend on that hold-up tray before it leaves. Okay. All right, and then you could rewrite your ODE. So if you divide it by L, for example, you get a tau. So then you can see tau dxi dt equals S, stripping factor, xi minus 1 minus 1 plus S xi plus xi plus 1. So we've rewritten in terms of the stripping factor and the residence time of the liquid on the tray. Okay. So now instead of having three variables, H, A, G, and L, we have two parameters, tau and S, the stripping factor, liquid residence on the tray. And remember, these are all coupled, so this is really just for stage I. So this is where these equations come from that you'll use in your studio, and you'll explore those more in your studio.